So this is our review for test number 4, which is in chapter homework 7 and 8. So this has to do with rotational systems. And what you have to remember is, instead of having x or delta x, acceleration, velocity, initial velocity, and time, for the rotating system we have delta theta, we have alpha, we have omega, omega 0, and t. So the only commonality is t. But for constant angular acceleration problems, we have the 4 equations that apply. So of course you'll want to write these down. So the 4 equations are delta theta is equal to omega plus omega 0, where omega 0 is the initial angular velocity, and omega is the final angular velocity, times t. We have omega, the angular velocity, is equal to the initial angular velocity plus the angular acceleration, which is constant, times t. We have delta theta, which is equal to omega 0 times t plus 1/2 alpha t squared. And finally we have omega squared is equal to omega 0 squared plus 2 alpha delta theta. So those are the equivalent ones in the angular system. And remember that delta theta is in radians. So if you were asked to calculate or given information instead of radians, you might be given in revolutions. We have the conversion that there are 2 pi radians per 1 revolution. You also have that, omega, which is the angular velocity. So delta theta is your angular displacement. As units of radians. Omega is your angular velocity. And it has units of radians per second. Sometimes I might give you an answer in revolutions per minute. You're very rarely given in the real world the speed in radians per second, but you are given in revolutions per minute. So to convert revolutions per minute, say to convert revolutions per minute to radians per second, you would take, as an example, let's say you're given 20 revolutions per minute. We use RPM for that. So that's what it's given in, but I'm going to write it out so you can rewrite it as revolutions per minute. So you have minutes per second, or seconds, 60 seconds per minute, and you have 2 pi radians per revolution. I used that earlier. And so it's usually a factor of about 10, a factor of 10 less. Because you can see we have 2 pi, which is around 6, divided by 60. So it's about a factor of 10, not exactly. 20 times 2 times pi divided by 60 is 2.09 radians per second. So make sure you convert that. If the problem gives us revolutions per minute, you need to convert to radians per second before you use that. And to go the other way, you would just use the opposite of that. So if I needed the answer in revolutions per minute, then you calculate a radians per second, you'd multiply by 16 divided by 2 pi. I think we've done enough of these. The basic idea is you have to find 3 out of the 5 quantities, and we've only really done one-dimensional constant acceleration problems, constant angular acceleration problems. So there will be a problem like that on there. It's going to be pretty simple. I think most of you get it. The second thing we covered in that particular chapter was this gravitational attraction and also in relationship to satellites. And a satellite can be a man-made satellite or it can be a natural satellite. So it could be the Earth rotating around the Sun, it could be the Moon rotating around the Earth, it could be a satellite rotating around the Earth, it could be a satellite rotating around a planet other than the Earth. And the key thing here is we have Newton's second law applied to this arrangement. So we usually have one big thing, like the mass of the Earth, and then we have a small thing, like the Moon or satellite. And there is a distance from the center of the planet to the object. So, like with satellites, small satellites around the Earth, you have the radius from the center of the Earth to the surface of the Earth, and then you have the height from the surface to the satellite. So you got to make sure you take that into consideration. So the total distance here we'll call r. And remember, r is radius, but it's really the distance between the two centers of the two objects. You have the radius of, I'm just going to put E to stand for Earth in this case, which is this distance right here. And then you have the distance above the planet right there. So you can see that r is equal to r sub E plus h, or any variation of that. So Newton's law of universal gravitation says there's a force of attraction between two bodies which is equal to the universal gravitational constant times m1 times m2, these are the masses of the two bodies, divided by the distance from the centers of the two bodies. So that's what those are. And G is, it's in your book, but since I'm not letting you use your book, I'll give it to you, right, and you can write it down so that you don't forget it. I don't have to give it to you. So it's 6.67 times 10 to the minus 11 newtons per meter squared, kilogram squared, or actually Newton meter squared per kilogram squared. And we could have figured that out because if we solve for G, you're going to have newtons meter squared per kilogram squared. Okay, so that's universal gravitational constant. So when you have a planet or a satellite orbiting, or moon orbiting something else, something that's large, you have this balance between the centripetal, well, you really don't have balance, you have a balance between the force, which is the gravitational force, and the centripetal acceleration. So we have the force, which is mg, m1, m2, this is using Newton's second law. Force, sum of the forces, and there's only one force acting on this, this is the force of gravitation, is equal to mass times acceleration. So we have the mass, and I'm going to call m1 being the mass of the object that's rotating, and it's rotating at some velocity v here, and we'll come back to that in a second. So you have m times acceleration, but the acceleration of an object in a circle is the centripetal acceleration, which is equal to the tangential velocity squared. So this is the tangential velocity divided by r. So you can see the mass of the satellite doesn't come into play in this balance. We also have, this is equal to m1 times omega squared. times r, r times r. So there's two versions you can come up with. One is g times m, and I'll put m sub e, assume it's the Earth, or whatever. This is the planet, the sun, whatever is at the center of this rotation, divided by r. Now notice you have r squared here, so you can cancel one of those out with one of those. So we get g m sub e times r is equal to the tangential velocity squared divided by 1. Okay, so we can just get rid of that 1. So there's that one equation there that relates the tangential velocity to the radius of the orbit, the mass of the object at the center of rotation, and the gravitational constant. You can also take this one and you can come up with a similar type of result. Notice you're going to have r cubed because you don't have r in both in the denominator. So in that case you have g times m sub e divided by r cubed equals omega squared. So that's another version you can use. It's the same basic idea. And the third relationship that you may need to use is that the tangential velocity is equal to omega, the rotational, the angular velocity times the radius, the same r, the distance between the centers of the planets. So that's the third equation. You really only need to use 2 out of the 3, possibly. So, there are various scenarios you can have. I could give you the mass of the thing that's rotating around. I could give you the radius, and then you could calculate either the tangential velocity or the angular velocity. Because you can see if I know this and I know that, then I can take the square root of that and solve for the tangential velocity. I could give you the mass and the velocity, and you could calculate r. So in this case, again, this is always 6.67 times 10 to the 11th, negative 11th. And so if I give you the mass of the thing rotating around, what it's rotating around, and I give you the tangential velocity, then you can calculate r. Now there actually is one more thing, because if you have a satellite or a moon, I think I spelled that wrong. Satellite. You have the period, which is the time for one rotation. So if you think about just from the definition of velocity, and we're talking about in this case the tangential velocity of the satellite, it's going to be equal to the distance divided by the time it takes. Well, the time it takes is this period. So let's designate the period as t. You're going to have to convert it to seconds. So if it's in days, you need to always convert to seconds. So let's just put that, convert to time, the period to seconds. So make sure you know how to convert days to seconds and hours to seconds, minutes to seconds. Okay, so the distance is going to be 2 pi times r, the radius. That's the radius from the centers of the two things, divided by the time, which is the period. So that's kind of the third thing you need to know. So with three of those things, you should be able to solve any problem that I give you. You just have to, you know, for example, if I gave you the, you know, I could give you, say, I have a satellite. I'm just going to give an example here. Let's say a satellite around Earth. So that means I'd have to give you the mass of the Earth because I don't let you have the book. So you're given the mass of the Earth, and if I give you the radius of the radius of the satellite, and I could either give you that directly or I could give you the height, and you could calculate. I could give you the radius of the Earth, and you could add the elevation. So if you're given the radius of the satellite, then you can calculate the linear speed, because one of the questions might be, you know, if I have a satellite that is so many kilometers above the surface, which would be h, and I give you the radius of the Earth, you can add this together to get this radius. You can use this relationship here to calculate the tangential velocity, because I've given you the mass, the other radius, so you can calculate, so you know how fast it is. And you know, the key thing, if you remember, is that satellites have to be moving pretty fast, or a space station has to be moving really fast. That's why you have rockets, to get them up to that speed. The other kind of problem I might give you is I give you the radius. And one of the special cases is geosynchronous orbits. And what geosynchronous orbit is, that the period of rotation is equal to the period of one revolution of whatever it's rotating around. So, you know, as an example here, you know, if I wanted a geosynchronous orbit for a satellite around the Earth, I would know that the period is equal to, from geosynchronous, I know the period was equal to 1 day. And so if you take 1 day and you figure out how many seconds, well, there's 60 seconds in a minute, times 60 minutes in an hour, times 24, which is 8,640 seconds. So knowing the period, I can calculate the tangential velocity. It's going to be, actually you can't do that immediately, because what I'm asking you for is to figure out what radius this thing has to happen at. So I actually have to do some substitution here. So what I can do is I can go back here and take this expression. So if I take the relationship that the gravitational constant times the mass of the Earth divided by the radius equals the tangential velocity squared, what I'm looking for is the radius, and then you can calculate v. So in this case, you've got that equation. You also have that the tangential velocity is equal to 2 pi r divided by the period. Okay, so for a geosynchronous orbit, I can plug that in there, and you'll have g times the mass of the Earth divided by the radius is equal to 2 pi r divided by the period, whole thing squared. And now, if I've given you the mass of the Earth, which I would give you if I had a problem, that, I have to give you the mass of the thing that it's rotating around. The mass of the Earth is, so I would give you mass of the Earth is 5.98 times 10 to the 24th kilograms. So I know that, I know G, I know T because I just calculated here. You can see I can solve for R, so let's just do that. So I get 4 pi squared R squared divided by T squared. And then because these are just pure ratios, I can do a little magic here, and I can take G times M sub E times T squared. So I move this from the numerator to the denominator to the numerator. So I get G M sub E T squared is equal to, and then I multiply basically I'm cross multiplying here, and you get 4 pi squared R cubed. And so R cubed is equal to G M sub E T squared divided by 4 pi squared. And then you can take the cube root of that to solve for the radius. And that is the distance from the center of the Earth, in this case, to the center of the satellite. So G is 6 point whatever it was, 6.67 times 10 to the minus 11th. The mass of the Earth is 5.98 times 10 to the 24th. The period is 86,400 seconds. You square that, you divide by 4, and you divide by pi squared, and take the cube root, and that'll give you the radius. Then once you have the radius, you could go back here and calculate the tangential velocity needed for a geosynchronous orbit. So that's how a geosynchronous orbit, I'm giving you actually the period, which allows us to have enough information from this to substitute into here where we only have one unknown, which is the radius. Okay, so those are the kind of things you need to be prepared for as far as the gravitational force in satellites. Now, there's the general centripetal acceleration. So centripetal acceleration happens when you have an object that's moving in a circle of some sort. And it doesn't have to be attached. You could have a car going in a circle. You could have a planet going in a circle. You can actually have an attachment where you'd have a ball on the end of a string going in a circle. So anything going in a circle, you need an acceleration to cause the thing to move, change direction consistently and constantly. And when we derived it, we came up with the centripetal acceleration is the tangential velocity squared divided by r, or it's equal to the angular velocity times squared times r. So those are the equations for centripetal acceleration. So, there are, you can use this acceleration in conjunction with Newton's second law to solve problems that involve things moving in circles. We use that over here for the case of a planet. But let's think about, if you've got something on a string, you might ask, what is the tension in the cable? So there's this force that's being on the string. For planets, it's gravitational force. But in this case, you have to provide the force, the necessary force to have it occur. So if I asked you, let's say I gave you that you're spinning it at 20 RPM. That'd be pretty fast. And the mass, I'd have to give you the mass. The mass is, say, 3 kilograms. That'd be a heavy mass. And I ask you, what is the radius? I'd have to give you the radius, let's say, is 0.5 meters. Let's give you the centimeters. So let's say it's 50 centimeters. and I ask you, what is the force? Force question mark. Well, the only force acting on this ball or this weight is the force which is in the tension in the string. So you would use Newton's second law, which would say force equals mass times acceleration, and because it's a special case of centripetal circular motion, we know that the force, the acceleration has to be omega squared r, or v tangential squared over r. So which one makes the most sense? Well, I give you the speed. It's in the wrong unit, so we have to convert that. So you'd say omega is 20 revolutions per minute, and you would multiply by 2 pi, divide by 60, and you would get 2 times pi divided by 60 times 20, so it's going to be around 2, a little more than 2, 2.1 radians per second. So that's your angular speed. So the centripetal acceleration required for that to happen is omega squared r. So we just plug omega, 2.1 radians per second squared times the radius, which is 0.5 meters. 2.1 squared times 0.5 is, so the centripetal acceleration is 2.21, and because this is a linear acceleration, it's not an angular acceleration, it's equal to meters per second squared. Okay. Then all you have to do is apply this to find the tension of the rope. It's the mass, which is 3 kilograms, times the centripetal acceleration, which is 2.21 meters per second squared. So you take 2.21 and multiply by 3 kilograms, and you get a force of 6.6 newtons. So, you know, those are kind of things that you might have beyond planets. Okay, so that was chapter 7 homework. In chapter 8 we had, instead of having the sum of the forces equals mass times acceleration, we have the sum of the torques equals the moment of inertia times alpha. And remember, the torque is equal to a force acting through a distance. Now, we didn't look at it, but you know, if the angle of this force is not perpendicular to the radius from the center of rotation, then you have to take into account the sine of theta. For most of the cases, we did it where this force was perpendicular to the radius, and therefore it's just simplifies down to force times distance. So we had this thing to just define torque in terms of force and distance. Moment arm. Remember, the moment of inertia for a point mass is equal to the mass of the object times the radius. That's the distance from the center of rotation to the where the mass is. And then we also had one for a disk, which said the moment of inertia is equal to 1/2 the total mass of the disks times the outside radius of the disk squared. So those are what the moment of inertias are for these two particular cases. So what I'm going to tell you is, you know, we did these problems in class, and I'm not going to work through one today, but we had the case, you know, of the disk, and from the disk we're hanging one or two masses. So we had two things that were moving linearly, which were the masses, and we had one thing that wasn't moving linearly but was rotating. These are not rotating. This is rotating. So we looked at Newton's second law for the rotating object and Newton's second law for the hanging objects. And remember, you have, if you do draw free body diagrams of these three things, for the two hanging masses, you're going to have the tensions that are pulling up and the weights that are pulling down. So this, we'll call this object 1, this object 2, I'll call this object 3. So we have tension here, T1, and then we have W1, and we have T2, and we have W2. So if we sum the forces in the y direction, it's going to be equal to the mass of 1 times the linear acceleration of 1. It's the same thing over here. And if you look at the disk here, what you have is you have the two tensions pulling down, which are going to create a torque around the center of rotation. So this is T1, this is T2. Remember, counterclockwise is positive torque and positive rotation. So T1 would cause a negative or positive torque, and T2 would create a negative torque. And so you have some of the forces in these ones, you have some of the torques. This has a moment of inertia, I. It also has a mass m, which is used to calculate the moment of inertia, and this has a radius r. We'll use capital R, which you can use the mass and the radius to calculate the moment of inertia. And so anyway, we do some problems in homework. We do them in class. So I'm just letting you know what kind of problem is going to be in there. Now, why do I emphasize this particular problem so much? It's because the this arrangement will give you a constant torque as these masses fall. They're going to give you constant tension. Everything's constant. Other examples of problems that I could do is I could give you, somebody pushing on a wheel at the periphery like this to cause this thing to rotate. But if you think about it, somebody to push this at a constant thing, they'd have to run around this, and it would be speeding. It would be accelerating, and so you'd have to run faster and faster and faster, and that really doesn't happen. The most practical case is where this would be attached to a shaft, and you would be providing a torque through the center of the thing. But that is kind of trivial. So this scenario is the best example of a practical, we've done it in class, so we know it works, of a case where you have both the relationship between the angular properties and the linear properties. That's the other thing. Don't forget, if I define y positive for these two, and this is positive counterclockwise, in this case, A1 would be equal to, so if this goes up, that's positive linear acceleration. That's going to cause that to go clockwise. So it's going to be negative alpha times r. And A2, when this goes up, it's going to cause this thing to rotate. If this, if this gets shorter, it's going to cause this thing to rotate counterclockwise, and so it's positive alpha times r. So you need that when you solve this kind of problem. Anyway, you'll have something like this on the test. And then, so what have we got so far? Constant angular acceleration problems. We don't know where the acceleration comes from, but we know that it's constant. We can use those 4 equations. The second thing is centripetal acceleration and its applicability to planets. The third thing that we're looking at is this case where we have acceleration of both the disk and the linear thing. So the fourth kind of problem is one we did in class. So again, I'm not going to go into a huge amount of detail on this, but we had a beam, and we did the lab where everything was just up and down, which is too easy. So I want you to be able to solve a problem like this, where you have a beam that's anchored in the wall, and there's going to be a reaction force in the x direction here. There's going to be a reaction force in here, and there's going to be a cable that either goes this way or it could go over to another wall over here. And then there are going to be masses that are sitting on this beam. So remember, what you do is you're going to sum the torques around this point, which means these two forces disappear. And you're going to break this force through the cable up into two components. So if it's going this way, you're going to have a positive y component and a negative x component. If it's going this direction, you're going to have a positive x and a positive y component. Theoretically, I could pull down this way or that way, but that would be kind of a self-defeating scenario. You could still do the problem. It's just that it wouldn't make any sense practically to do something like that. So, when we do the sum of the torques around this point, the only one, well, not the only one, you're going to have the y component of this cable is going to give you a torque, and the weights that are going to be sitting on here, the weight of the beam, which is in the middle, the mass, the weight of the beam, and then you're going to have masses that are going to be located along the beam, and you sum the torques around it, and the only unknown that you're going to have is the y value of this support thing. Once you have the y value of the cable, you can just use geometry to find the total tension and the x component. The only x components are going to come from the support force and the x component of the cable. And then finally, to solve for this reaction force here, you're going to use the sum of the forces in the y direction. So you'll have this y pulling up here, the y component of the cable, and then you'll have the y values for each of the masses, including the mass of the beam. And the only unknown will be this final force in the y direction. So you don't have to use substitution or anything like that. It all works out. So let me just reiterate the procedure. You would sum torques around, we'll call this point 0, around 0. From that, you can solve for the y component of the tension in this cable. Okay, so once you do that, then you can solve for t sub x and t sub y, because you're going to know the geometry. You're either going to have a force triangle that's going this way if it's this support, or you're going to have a force triangle that's going this way if it's this support. So if you have this support, you actually have to, this force will be going this way to counteract the force that goes that way. And so, what you're going to figure out is t sub y here, and this, so I can move this over here and make the triangle. So this is, this is t sub y, and if you know what this angle here is, theta, and this is t, and this is t sub x, you can just use right triangle geometry. The sine is this divided by that, So you can calculate this, and the tangent is this divided by that. So you can use the tangent to find t sub x. Okay, so you've solved for t sub x. And so then you use the sum of the forces in the x direction, being 0. Up here, in the first case, we have the sum of the torques around 0 equals 0. That's what we're using up there. Sum of the forces in the x direction, you can calculate r sub x, because there's only two forces, this one and that one. And then you can use sum of the forces in the y direction are equal to 0 to solve for r sub y. Because at that point, when you get to here, you're going to know this y component, you're going to know all the weights. And remember, when we do the sum of the torques around here, anything that causes this thing to rotate clockwise is a negative torque. Anything that causes it to want to rotate this way is a positive torque. So you can make sure you get your signs right. Okay, and then the final problem is conservation of angular momentum. So remember, angular momentum is the product of the moment of inertia times omega. So you have the initial moment of inertia times the initial angular velocity is equal to the final moment of inertia times the final angular velocity. So, typically what happens in these kinds of problems is you have the skater type problem where the person takes their arms in and changes the moment of inertia of the body. Or you can have the case where you drop something on a rotating disc. So you have this rotating disc, it's rotating into the plane of the picture, and you take a blob of something or a parachute as to whatever it is, and it comes down. This initially, as it drops vertically, doesn't have any angular momentum, but when it lands on the disc rotating, it'll start to rotate with the disc. So this, you have the moment of inertia of the disc initially, and then you drop this blob on here, and then you have the moment of inertia of the disc plus the moment of inertia of the object. So in this case, the final moment of inertia is greater than the initial moment of inertia. So for the disk example, the initial moment of inertia would be equal to 1/2 the mass of the disk times the radius of the disk. Whereas the final moment of inertia would be the same moment of inertia of the disk, but you would have the mass of the person, or whatever this thing is, times r squared. So this gets bigger because this is the same, and then you add more, so the thing slows down. Whereas with the ice skater, you have, say, the person's body, and then you consider the arms as a separate part. So initially, you've got the moment of inertia of this part plus the moment of inertia of that part, and then what happens is the person brings their arms in. So instead of having that, you might have something that's like that. Same mass, but it's moved into the center. And so the initial moment of inertia is larger than the final moment of inertia. In that case, the thing speeds up as they move their hands in. So in pretty much all of these cases, what we're doing is we're changing the moment of inertia by doing something, dropping a blob on the thing, dropping a disc on top of another disc, moving our arms in. You have two people out in space that are connected by a rope. So if you pull them closer together, you're decreasing the moment of inertia. So those are the kind of scenarios that you should be able to address. And we looked at all of this in class. We had the disc falling on the other disc, which was in the lab. We did the problem where we dropped the blob onto the disc. We've done the ice skater, where you bring your arms in to lower the moment of inertia. And we've also done the case where you've moved these two things closer together. So, they're considered point masses, but the radius as the radius is reduced, things spins faster. Or if I had rope and I just let go of, if I reduce let the rope slip through my hands, then if these went further apart, then they'd slow down. And all of them, you can solve for the final velocity, angular velocity, by just taking this and dividing by that. So usually it's a matter of evaluating this difference in moment of inertia from the beginning to the end. The last thing that we also talked about, but we're actually not going to do in the test, but I'm just mentioning, is if you have something that's rotating, the rotating object has a moment of inertia, it has a kinetic energy, which is equal to 1/2 the moment of inertia times the angular velocity squared. So we looked at that with this case of the space people connected by the rope, and we saw that as we pull these people close together that they sped up, so they got more kinetic energy, and that kinetic energy came from the work done as these people pulled together. We also looked at, in this case, when you drop the blob on here, you're going to lose some kinetic energy because of the interaction between the disk and the blob as it forms so that it can connect itself to the disk, so you can calculate changes in kinetic energy. We also did it with the thing rolling down the incline, where we solved this problem using energy considerations. But I'm not going to put that on the test, but that's something else that we learned. So that's pretty much it. 5 problems. One is involving one of these constant acceleration problems. So using these 4 equations, so make sure you write those down. The second problem involves satellite. So write this down on your cheat sheet, these equations. Make sure you understand what they stand for. Don't just write them down without understanding. You might want to write what these stand for. Universal gravitational constant, the mass of the, in this case, Earth, but whatever the mass is of the object at the center of rotation. So if I go to Jupiter or Mars, you'd use the mass of Mars or Jupiter. And then you have the relationship between tangential and angular velocity. You also just have the way to calculate tangential velocity based on the period and the radius of the object that's rotating. Just some simple centripetal acceleration problems. Make sure you know how to convert revolutions per minute to radians per second. Then we had Newton's second law applied to rotating objects. Instead of using mass and acceleration, we use moment of inertia and angular acceleration. The torque is not just a force, it's the force acting through a distance. If it causes something to rotate counterclockwise, we consider that a positive torque. If it causes it to go clockwise, that's a negative torque. The moment of inertia is important for rotating systems, which not only depends upon the mass of the object, but where the mass is distributed. We've gone through a couple of iterations of this type of problem, so we are able to relate the linear and the rotating properties through this relationship, because the rope, which moves up and down, is also connected to the outside of this pulley. So this linear motion changes into rotating motion through these relationships. And then you do the sum of the forces and the sum of the torques, and you can end up with you can be able to solve for alpha. If you know alpha, you can then solve for the tensions. We did a lot of those problems. Then we have our rotational equilibrium problem, where you initially use the sum of the torques around this point where we have the most unknowns, and we can use this procedure to solve back for all the unknowns: the tension of the cable, the 2 reaction forces on the wall. we use geometry to relate. Once we know one of these three, we can calculate the other two, since we'll know the angle of the forces. And then we have conservation of angular momentum, where there are no external torques applied. All of the torques are applied internally. You know, as this ball drops on here, this blob drops on here, the parachutist drops on here, there is a force between the disk and the person as this person goes from 0 angular speed to a given final angular speed. But those 4 torques are occurring internally, so we can still use conservation of angular momentum to predict how much the final angular velocity is affected by the change in moment of inertia in these different types of scenarios that we've talked about in class. And that's it.